today I'm here to tell you a little bit about our speaker, Dr. Steven Chu from Stanford University. Let us face it, we all know who he is. Nobel laureate in physics in 1997, Secretary of Energy for President Obama's first term. As tempting as it is to stand here and tell you more about his stellar achievements, I've decided not to do it. So instead, I'm yielding my 2 minutes to you so you can spend a little bit more time with him. So I'm not going to tell you about his 32 honorary degrees, or 15 patents, or 35 awards and honors. So here is Professor Chu.
All right, thank you. It's a pleasure to be here and to talk to you about something I hope you all care deeply about. Certainly I do. And so I hope I can teach you a little new things about this, but the summary, and I apologize for 2 things. First, that's slightly out of focus. And let's zoom, that's better. And the lights, but that's life, can't do that. So I'm going to talk a little bit about climate change and where we're heading, and but spend most of my time talking about possible solutions. Not all of these are commercially viable yet, but it will give us better choices. So first, climate change and where we're heading. Now, I'm sure all of you know, have seen records of the surface temperature of land and ocean. These happen to be records from 1850 to 2017. And most people would look at that data and says, the temperature seems to be rising. Most people. When I was in Washington, D.C., there was a lot of noise made about this plateau here and said, see, it's not rising. And in any case, I do want to point out that much of the temperature rise, the large fraction of it, maybe 4/5 of it, occurred only since about 1975. So you talk about before the Industrial Revolution times, but it's actually only in the last part of the last century and this century. What is it due to? Well, there's very, very compelling evidence that it's due to an increase in the amount of CO2 in the atmosphere, carbon in general, and also methane. And if you look at what has happened over the last, well, I'm actually taking this back to 1 AD, and you see that the carbon dioxide has been pretty constant for the last couple thousand years, almost 2,000 years, until it started shooting up. And so now, the rise in carbon dioxide that we measure is actually in quantitative agreement with the estimates of how much carbon we put in the atmosphere due to human activity, both in the form of fossil fuel burning, also methane emissions from our agriculture, livestock, and also greenhouse gases due to agriculture. So, but the smoking gun, which you may not know about, is that you can actually measure the carbon dioxide in the atmosphere of a particular ratio of carbon 12 to carbon 14. Carbon 14 is radioactive. It's made in the upper atmosphere, and it mixes with all the stuff in the biosphere. It's made by cosmic rays in the upper atmosphere. The half-life is 5,700 years. So you have carbon 14 in you, but suppose you die and they put you in a really good coffin and they put you on the ground and you're isolated from the biosphere. And perhaps many lifetimes of carbon 14 later, there's no more carbon 14 in you, because you're no longer exchanging carbon with the environment. So they take you up and all your friends and family and burn you for fossil energy. The carbon you emit or your people using your remains won't have any carbon 14 in it. If there's enough carbon 14 that's non-carbon 14 that's released, then the ratio of carbon-14 to carbon-12 gets diluted. Okay, let me say it again. If you take a bunch of carbon sequestered for many lifetimes of carbon-14, which is now 10,000, 20,000 years or longer, and then take all that carbon, scoop it up and throw it in the atmosphere, it's no longer connected with trees. It's no longer connected with vegetation, right? Because that life cycle is 100 years, 200 years, several hundred years, not 10,000 years. That quantitatively agrees with fossil fuel emission. The fossil fuel has been sequestered from the environment for a long time. So this is what most scientists consider the smoking gun. It cannot be just natural carbon from the biosphere just suddenly bubbling up. And it also makes quantitative agreement with what we know, as does the raw carbon. So it's because of that that we know that this increase in carbon dioxide is due to humans. Now, let me step back a little bit and take a bigger picture of where we are. And if you compare us, Earth, in the middle to Mars and to Venus, what you find is the average temperature of the globe is about 19 degrees centigrade. 20 degrees centigrade, 22 degrees centigrade is considered room temperature. Mars is very cold. It's slightly smaller mass. It has very much, a very, very small fraction of an atmosphere. Venus turns out to be a lot hotter. The pressure of Venus, because it has this very thick, mostly carbon dioxide atmosphere, is 90 times the atmospheric pressure of Earth. Mars has just a wispy, thin atmosphere. Its pressure is 0.006 of Earth. And of course, we're at 1 atmosphere, and we have this lovely mixture of mostly nitrogen gas and oxygen. Venus is essentially all carbon dioxide, and so on and so forth. So we happen to be in a very special place where lots of liquid water is available. And liquid water there are two things essential for life: liquid water and some source of energy. It doesn't have to be solar energy. It could be, chemical energy from oxidation states of iron that life can feed on. But it does need water, as far as we know. Mars no longer has any water on its surface. It used to, no longer has. Venus doesn't have any water on its surface, not liquid water, because it's just way too hot. So anyway, now you come a little closer and look at Earth, and then you realize all of life on Earth is actually in a very teeny tiny layer, a few kilometers thick. Okay? Very little life, the oceans go maybe 2 to 6 kilometers deep. The deepest is 10,000 kilometers, but most of life in the ocean is in the upper fraction of a kilometer. And the atmosphere, by the time you're in the stratosphere, only 50,000 feet, most of the air is below, virtually all the water vapor is below. And so think of Mount Everest, 27,000 feet. There's not much life there. Okay, so think about where life is. It's in this little thin atmosphere that you see there. All right. And so, and this is a picture of the space shuttle, and just to drive home this point, the troposphere is only 10 kilometers high, 75% of the air mass, 99% of the water vapor. I'm focusing on water because it's so precious to life. And so there's where we are. Now, we used to think the Earth started in a very bad place. Super, super hot. Lava being bombarded by meteorites, things of that nature. And the wonderful thing about science is this was great, and it was called the Hadean Earth, after Hades, because it looked like hell. But it turned out, by looking at the fossil record, there are zirconium minerals that are formed, and they formed actually very, very soon after the birth of life. We're 4.5 billion years old. Within the first 500 million years, there's evidence that there was water on the planet. Okay? So it got hospitable very, very quickly. And then with liquid water, then you can have life. All right, so now, talk a little bit more about water. You can ask, are glaciers melting? Is the sea level rising? The short answer is yes. You can go around and take pictures of glaciers. This is Muir Glacier, Alaska, 1941. Muir Glacier, Alaska, 2004. And you say, that looks different. It looks a little warmer on the right-hand side. And you can take pictures of lots of glaciers all around the Earth, but there's a better way of doing it. And the better way of doing it is actually to use satellites. And what happens is the United States has put up a pair of satellites. Europe has another pair. And if this is the Earth, it's rotating, and they go around on a polar orbit. So as they go around this orbit, the Earth rotates under it, so they get to watch everything on the entire planet. And what they do is they look at the wobbles of these two satellite orbits due to local changes in gravity. So if, for example, in this cartoon, these satellites are about to go over Greenland, if the mass of Greenland has changed a little bit, it will see a slight change in the orbit. And this was actually rose out of technology in the Cold War when the United States and the Soviet Union were trying to kill each other with 35,000 warheads apiece. Each 100 kiloton average detonation, Hiroshima was 15 kilotons. And so we had about 10,000 tons of TNT for every man, woman, child in the United States and Soviet Union if you just spread it out. Luckily, we so far have not used that. We're gone down in armament, but while they were trying to do this, and they were trying to throw ballistically these warheads halfway around the world, but the launch time was only a few minutes. So they would just have really accurate throwing, and it would just lob it over there, and then you notice, oops, changes in the gravity made the orbits wobble, and they wouldn't be accurate. And then they wanted to put these 100,000 kilotons of H-bombs within 50 yards of something. So they began to map changes in gravity. But now someone else turned it around and said, oops, if you have changes in mass, then you have changes in gravity, you have changes in orbits. Why not measure the change in the orbit and see if you can back calculate? And that's what we now do. So now, as the ice melts in Greenland, the weight on it is less, so the land springs up, it's elastic. So in addition to measuring the perturbations in the orbits, you actually have to measure the distance from the satellites to the ice. And so all of these things are measured to fractions of a millimeter. The distance between these two satellites is measured to the width of a human hair. And from that, you can back out changes in the ice mass that are in the millimeter per year range, which is pretty spectacular because the glaciers in Greenland are 2 kilometers thick. All right. So what does it tell us? It tells us something that surprised the climate people until these measurements were made. And where you see black and orange, you see loss of ice mass. And the blue curve on the lower, let's see if I can have anyway, the lower left-hand side is the average of Antarctica. The surprise was it was expected that the ice mass in Antarctica would increase, not decrease. Because a warmer planet meant more evaporation, meant more, in the case of Antarctica, more snow and ice forming. But it's so cold it doesn't melt. So we expected Antarctica to increase in ice mass, but in actual fact it's decreasing. There's a little bit of increases where you see blue, it's increasing, but only in the first part of this data from 2002 to 2016. But the whole of the ice is decreasing and it's accelerating. And that's very scary. Some of the glaciers in Antarctica are running off now at about 1 kilometer per year. So it gives you a new meaning to glacial speed. So there are little rivers going off, and it turns out we're beginning to understand why. It's actually connected with the melting in the northern hemisphere. But before I do that, I just want to also remind you, as a matter of historical record, if you look back into the last warm period of the Earth, which was about 116,000 years ago, where the temperature on average was about 1 degree warmer than today, or roughly speaking, the UN goal, and you ask what was the sea level during that period of time, the answer was about 6 to 9 meters higher, not centimeters. Okay? But we used to think it would take several thousand years to get 6 to 9 meters higher. And now all of a sudden all bets are off because the ice is melting far faster than we thought. Okay? And so now we think maybe not this century. This century is probably going to be less than a meter, but next century another couple of meters, and by a century and a half you're in the 3-5 meter range. 10 meters would be very bad news. 5 meters would be very bad news. 1/10 of the human population lives within 10 meters of sea level. Okay. Anyway, so that's a matter of record. That is not a climate model. And how we measured that is simple. It's again radioactive dating. You look at where the critters, the seashell critters who live at the border of land and ocean, when they died, you can date. And where were they when they died? And you look all around the world because land rises and falls as well locally. So you average around the world and you get this 6 to 9 meters higher. So it's just historical record that says, well, if we get to these temperatures and you hang around for a couple hundred years, you're in a very bad place. It turns out we are now beginning to understand why Antarctica was melting, and it's really bizarre. On the left-hand side is a photograph of the Gulf Stream, a thermal photograph. And you see it coming off and going towards the north, and then it goes from the Gulf Stream into what's called the North Atlantic circulation. On the right-hand side, you see that orange curve over here, all right? And as the warm water rises, this is very warm water, it cools and it sinks. And then it sinks and it goes below, and the return path is now deeper in the ocean going back towards the South Pole. All right. So that's what's happening. But what is happening is because Greenland is melting, because the frozen Arctic Ocean is mostly freshwater, so the North Atlantic is becoming fresher, means it's less dense. So this water from the Gulf Stream that used to go down, get cold, and come back is, yes, it's going down, it's getting cold, but it's not getting quite as cold, and it doesn't sink as far because there's fresh water. Okay, and then so the return path from the northern hemisphere over here means that that North Atlantic return path that you see in that green is actually closer to the surface, it's warmer, and it's slowing down. And so now you have warmer water hitting Antarctica. And then warmer water hitting Antarctica does something really, in hindsight, duh, but wasn't again projected. There's Antarctica, there's ice on the land, and there's mountainous area. And then the ice actually descends into the ocean, and there's what's called a grounding line in this cartoon. This is below sea level, this is sea level. This warm water eats back at that. And so that ice in the ocean that's hitting the ground is being eaten back very rapidly, and we've been watching this over the last decade and a half. And so that's a friction point. Imagine ice on land goes clear into the water, and all of a sudden the friction down below the water is being eroded away, and so this starts to plastically slide faster. So this is what we call a commitment to faster glacial runoff because there's no longer as much friction. It doesn't have to melt, it just is plastic deformation. And what we're now thinking is some of these glaciers, once you start this thing going, it's like a slow-moving avalanche, and it just continues. So even if you hold at the same temperature, it will continue because the grounding line is eroded away. And so this is why the glaciers are running out faster. 20 years ago, might have been predicted, wasn't really appreciated, but now we see it for real, and it's a measurement. Okay? So that's where we are. If you look at where we are in time, we're over here at 2019, and this is the emission in billions of tons per year of CO2. This would be a business as usual scenario. And you say, well, let's forget about 1.5 degrees. That's essentially impossible. Let's just stay at 2 degrees. What do we need to do in order to limit the warming of the Earth to the 6 to 9 meter higher target? Okay? We're modifying our aspirations with some realism. And the answer is you have to follow this blue line, and which means you have to decrease carbon emissions dramatically starting about now. But you see where that 0 is? What does 0 mean? 0 means no carbon emissions everywhere in the world from everything. Electricity, transportation, agriculture, forestry, land use, everything has to go below 0 to stay at 2 degrees, 6 to 9 meters higher. Okay? Let me just let that sink in. The question is, will we get to 0 emissions by 2070, 2080? And the answer is no, of everything. Okay? Not just the US, the whole world. All right? So that's the 2 degree scenario. And so what I think probably we'll do is something like this, just wild guess, because we don't really know. We don't know how soon the world will wake up to that we're in real danger, but let's suppose it's like that. And so that's actually going to 3.5, 4 degrees, with big uncertainties on either side. It could be as small as 2.5, 3 degrees. It could be as much as 5 degrees. So we don't know. So let me also say that it's not emissions per year that matter, it's cumulative emissions. That means ever since humans started appearing, it's how much have we emitted in terms of all the carbon. And the reason it's cumulative emissions is because if you stick carbon dioxide, methane, and other things up in the atmosphere, the methane breaks down within a dozen or 2 dozen years to carbon dioxide. And so ultimately it's carbon dioxide that's the long-term stuff. The land and oceans absorb half of that in less than 10 years. You throw it up in there and the ocean gets more acidic, and soda water is slightly acidic, and the oceans have gotten 30% more acidic since 1800 or 1900 really. And land, because there's more carbon dioxide and it's a little bit warmer, there's more vegetation and it fixes more stuff. So the Earth actually responds by fixing roughly half the carbon. Okay, so that, by the way, goes into the accounting. It's not all the carbon we emitted is up in the atmosphere, only half of it. What about the other half? Well, it's got several lifetimes, but characteristic time is about 10,000 years. Okay? So 10,000 years is a long time. So if you say half of it gets absorbed and is already accounted for, the rest of this kind of lingers around for 10,000 years, then you actually want to do something that's less than the 10,000 year time scale. So that's why we do cumulative emissions. That red dotted line is the best climate prediction guess of staying below 2 degrees with a 60% probability, 2/3% probability. Where we're heading now, based on the current rate, not an increase in the rate of carbon emissions, and oh, by the way, it is increasing, but just the current rate, we'll pass that line in about 20 years. Okay? And let me also point out that 3/4 of the greenhouse gas emissions has occurred in the last 65 years, and we are still accelerating. And so the father of Taoism was reputed to say, he may not have said it, Yogi Berra could easily have said it, if you don't change direction, you'll end up where you're heading. And we are heading across that red line. Okay, how much across the red line, I don't know, but we are heading surely across that red line. All right. And then again, half the CO2 emitted is being to circulate for 10,000 years. So don't think of 2100, think of 12100. All right? It's not 100 years. 2100 is 100 years. It's 12100, right? You have to add another 0. And so we'll say that effectively, as far as we're concerned, that's a long time. So we have to fix this problem. All right, now let me tell you about some technical solutions. First, when you look for technical solutions, you have to look where the problem is. And it turns out that almost 30% of the greenhouse gas emissions are from agriculture, forestry, land use. And so the orange down there is due to fossil fuel emissions due to transportation, electricity generation, heating, steel making, all that other stuff. This CO2 over here is due to forestry, agriculture. This is methane, of which more than half of the methane is due to agriculture. It is not due to methane leaks from oil wells. And then N2O is actually due to fertilizer. If you over-fertilize, the plants don't pick it up. The N2O actually is a greenhouse gas, and it also makes algae blooms, but does all this stuff. And then there's a little bit of refrigerant gases. All right. So now, we've geoengineered the planet in a major way, because if you look at all the habitable land on Earth, take away the oceans, take away the Himalayas, things like that, half the land is under agricultural production or grazing land already. All right? Let me drive that home. And if you ask where all the carbon in life is on the Earth, it turns out most of the carbon is in plants. A big unknown is there's a lot of carbon in bacteria, but because bacteria are small and we haven't charted all the soils of the Earth, it's the biggest unknown. And then there are fungi and other things. That little corner in the lower, can you see my pointer here? Yeah. That little corner down here are called animals. So the animals are only a little sliver of all the carbon on the planet. But let's blow up this little sliver and ask, where is the carbon in the animals of the world? Well, it turns out that arthropods, and these are spiders and insects and millipedes and things like that, are the biggest amount. That's the stuff in red. Fish are the second biggest. Okay? But now I look down here and this little stuff where I've circled it, and I have three things. I have livestock that we eat, we have humans, and we have the rest. The rest is rats and mice and buffalo and elk and whatever, wild animals, okay? Livestock and human biomass is 96% of all mammals on Earth by weight. So we're not a little perturbation on the planet anymore. This is staggering how much, you know, there are no lions and tigers and bears, oh my stuff, walking around out there with herds of wild bison roaming around. It's only the stuff we eat and us. Okay? Now, we have not only bioengineered the planet from our agriculture and livestock raising, but we've also bioengineered plants, and we've been genetically modifying them for 4,000 years. And just to drive this home, the little thing, that dark thing on the left-hand side is wild corn, and these little things, but now you have examples of other corn which are kind of not recognizable. So the corn we eat doesn't look anything like wild corn. Similarly, those are the things in circles. That was what appeared in the wild. The animals we eat are really not like anything else either. If that full circle is the natural lifetime of beef or pigs or chickens or turkeys, the little red part is only the fraction where before they're slaughtered. So the animals which we raise are bred to grow very, very rapidly. For example, a pig before slaughter is only 22 to 26 weeks old, and by that time it's 280 pounds. Average size of a pig. Okay? And so, again, now, let me talk a little bit about these animals. Now, the turkeys are typically slaughtered in 3.5 months, and they're typical turkey of the wild, not wild, domesticated turkeys. These are some domesticated turkeys. they're weighing, in the Safeway supermarket, they're weighing about 14 pounds. So 3.5 months, 14 pounds. They actually, they can't grow to adulthood because they're so distorted and breast heavy that they won't grow to adulthood. They can't mate naturally because they're just so distorted. So the turkeys we eat are actually artificially inseminated. Okay? And they don't really look like wild turkeys. This is a wild turkey of unknown age, you know, but I'll tell you, they're probably not 3 to 4 months old. The only thing I can be sure of is I can tell you how old that wild turkey is. Wild Turkey 101 is aged, they claim, 8 years. Okay. So this is true of cattle, it's true of turkeys, it's true of chickens, it's true of pigs, it's true of everything. And if you look at the greenhouse gas emissions, CO2 emissions by regions of the world, number 1 is China, number 2 is the US. All of the EU is number 3. But if beef and dairy cattle were a country, they would be second only to China and the US in greenhouse gas emissions. More than the EU 28. Okay? It's staggering how much carbon dioxide and methane, and you know, we are trying to make more polite cattle that don't burp and fart methane. But right now, that's what they do, and they make a lot of methane, they make a lot of CO2, and a lot of land is used. About 10 times as much land is used to grow animal feed for the beef per kilogram of protein than what you can raise on crops, okay? So now, here's some potential technical solutions. There are 2 manufacturers of what we call artificial hamburger meat. This is not your average soy burger. One is called Beyond Meat Burger. You can buy it in Safeway here. The other is called Impossible Foods, which is impossible to buy. You have to go to a restaurant. And now there's really first-rate interesting chemistry. This is made from vegetable crop products. There is no meat in here. And I can guarantee you they really taste like a hamburger. I've cooked a couple Beyond Meats and I've got some Impossible Burgers. And for example, the red meat blood taste of the hamburger is because they got a vegetable to produce something that is related chemically to hemoglobin. It's from a soy plant, but it's actually the chemical, and they have another thing that's related to muscles called myosin. These are filaments, not because you want the texture of the muscle, but because when you heat up the myosin molecules, they release juices. So the stuff actually cooks and tastes like a hamburger, really a good hamburger, unless you overcook it. If you get Beyond Meat and you cook it to medium or well done, it tastes pretty crappy, but so does normal beef. So maybe that's not different. I think my wife was very skeptical, was sitting in the audience, you know, said, "How do you like this?" And you really cannot tell. Okay, so what is the dream? The dream is when you go to scale by growing plants, you actually have something that substitutes for meat. And then the carbon footprint of that would be much better. I don't think it's possible to legislate taste in people and habits. The good news is the younger generation, the 20-year-olds and the teens and a lot, if you know grandchildren and children, you know, there's a surprising number of vegans popping up all over the place. Okay, and so the younger generation is beginning to realize personal choices do matter. And so, but if you're older and you're used to eating meat your entire life, you're probably going to continue eating meat, even if your doctor says it's not good for you. So the good news is there may be a way of getting this. This is good for hamburger. They haven't figured out how to make steak yet. Okay, it's better than that. The plants themselves can be made more efficient. And again, it's genetic engineering. We've been genetically modifying the animals and the corn and everything we eat, but now we're saying let's genetically modify the microbes in the soil, and maybe the plants, but you start with the microbes in the soil so they can form a symbiotic relationship with, for example, this is corn. And so there are legumes that have this symbiotic relationship, and so they actually, through this relationship, the nitrogen doesn't come from fertilizer, it comes from atmospheric nitrogen getting into the soil, microbes making it, and ammonia-like compounds that are used by the plant. The plant says, hey, I'm hungry, I want another dose of nitrogen. They talk to the microbes. And it turns out you can actually make microbes that do this. It is being pursued by several companies. This is one, Pivot Bio, is in the Bay Area. And they're producing these microbes that eventually they're going to put on seeds, but they're undergoing final beta testing. So for this planting season 2019, they're going to release it commercially to farmers. And so they've been doing a couple of years of this, and the farmers like it. They don't have to spend as much for fertilizer, and it's much less of a carbon footprint. So if this can work commercially, get the farmers to make as much or more money, but without the ammonia fertilizer-based fertilizer, that's very good, because about 2% of the greenhouse gases comes from making fertilizer. And then when you over-fertilize, you get another wash of things. But if the microbes are making the fertilizer as the plant needs it, you won't have that. So the question is, can you do this not only for corn, can you do it for all the annual crops? Ultimately, you want to turn these annual crops into perennials. It's less of a, I talked to Pivot Bio, and they don't have a business model yet, because if you only plant once every 12 years, you want to sell them seeds every year. Right, but it's not so far-fetched. But for sure, the plants now can make their own nitrogen. Again, less carbon footprint. So you get more efficient plants, and you get artificial meat. All good things. Now, there's agricultural residue. The stuff we eat in plants is mostly seeds. Or fruits and things like that, which are around the seeds. And we throw the rest of the plant away. And so if you have wheat straw, if you have rice straw, if you have corn stover, half the corn stover you have to throw back in the land because that recycles a lot of the nutrients. But it turns out through studies that you can extract half of it. But all the wheat straw we now used to burn, no longer allowed to burn, you bury. That rots, turns to methane and carbon dioxide. So if you could convert agricultural residues into products, that would also be good. Now, what products do you want to, first you think of biofuels, but biofuels is competing against oil, and it's tough. Even at $100 a barrel, we still don't have biofuels that could be competitive with oil. But there are other things. And if you take a barrel of oil, about 85% of it is used in transportation, and it's a $3 trillion a year market around the world. 10%, 15 maybe, rising, of the oil is used to make chemicals and plastics. It too is a $3 trillion market. So think about this. You get a barrel of oil, you have 15% of it, and it makes as much money as the rest of the oil, mostly for transportation fuel. If you can find a substitute for plastics and chemicals, you've cut the value of oil in half. Okay? What do you want to do? You want to cut the value of oil so that it's no longer profitable to get it out of the ground. Okay? And the way you do that is you make, I'll talk a little bit about this, electric vehicles that will work better than conventional cars. You make chemicals and plastics with something that works better. And all of a sudden you look at the oil in the ground and said, why should I bring that up? It costs more money. It's stupid. Okay. Now, if you don't get something that's better than oil and natural gas, you will actually, that stuff will come out of the ground. Because if you're country and you're standing over, let's say, $100 or $10 trillion worth of money in the ground, it does come out. So the only way you really get rid of oil is, the old adage, I'm fond of saying, Shakyamani said the Stone Age didn't come to an end for lack of stones, and the Oil Age did not come to an end for lack of oil. And what it really meant by that is we don't look down on the ground and see a lot of stones, and then we don't think to ourselves, if it wasn't for regulators, we wouldn't have those stranded assets. Not every stone had to turn into something, because we went to metals. So what you'd like to have in a quote, an asset is no longer an asset. Okay, so ultimately that's going to have to happen. So now, talk about what we make stuff out of. It used to be, before the turn into the 20th century, we made stuff out of wood and fibers and things like that. They were natural products. And then oil was discovered, and it turned into a big business around going into the 20th century. And as oil was discovered and production rates increased and chemistry improvements increased, then you had the birth of chemicals due to oil. Virtually all the chemicals and plastics are from oil, and now natural gas. And so this explosion of all that stuff is happening. And then the question is, can you actually go back to using these agricultural residues and try to subvert that? And the verdict's not in. I'm on the board of a company in the Bay Area called Zymergen, and its purpose is to take microbes that you genetically modify, and you ask these microbes to make stuff, now valuable stuff. Now the microbes do make stuff that is in commercial use today. Soy sauce is made from microbes. MSG is made from microbes. A lot of the protein supplements, tryptophan, all this other stuff, is made in large scale, tons, from microbes. So there is industrial production of microbes. But the question is, can you get the microbes to make other stuff that would be valuable? And so it's a mixture of what do you want to make? Can you modify the bacteria, put in other genes to do this, and to have it make it in a good enough quantity? And in one case, this is really cute, the company made a chemical substance that another company wanted to make more of. We found through machine learning, adjusting all the genes of the entire microbe and robotics to get rid of the noise so the machine could find out what the best solution is. It turned out that you had to put in 14 new genes, of which 3 of them made sense to a biochemist. Yeah, that's part of the metabolic pathway. Another 5, if you look at a molecular biologist or a chemist and say, what does that have to do with what we're trying to make? And 3 of them, we didn't even know what the genes did. Okay, so the machine learning didn't have to know enough biology to know what the genes did. We just moved everything around and said, pick the best solution. Okay, so this is again a very, very powerful new technology that's emerging. And the cool thing is, what can you make? You can actually make safer insect repellents that don't have any of the bad ill effects of insect repellents. Nature has made waterproof glues that set in wet because mussels have to stick to rocks and they don't get to have a dry surface, prepare it, and right? And so what you want is that you can use microbes to make the chemicals that mussels make in biology that you can't make actually with synthetic organic chemistry. Because synthetic organic chemistry, especially from fossil fuels, only carbon and hydrogen, hydrocarbons. Biology uses all sorts of other things, nitrogen, oxygen, a little bit of sulfur, a little bit of that, okay? So you can make better wound healing things. So if you have a very bad burn, you can make better plastics like this. You can make thin films. Apple, we're entering into a contract with Apple because there's some thin films that they want on their cell phones. It's a very high value product. You can't make them through normal chemical means, but the microbes can make them. You start with the high value stuff, but in the end you do want to get to biofuels. But mostly what you want to do is you want to replace petroleum and natural gas as the feedstock for chemicals. Okay? And to have something renewable. Biomass, residual scrap biomass is renewable. Okay. So that's something I think is exciting. Now, I'm sure you all know this, but renewable energy around the world is getting a lot less expensive. And in the best sites in the world, let's say in Southern California, in Arizona, New Mexico, in the Middle East, Saharan Africa, fully installed solar without subsidy in the Middle East is about 2 cents a kilowatt hour, including profit, for the wholesale generation. And so in many, many places around the world, 2.5 cents a kilowatt hour at the best sites is highly likely. And the feeling is it's going to continue to go down. The technology for solar, even silicon solar, is still going to drop by a factor 2 in cost. So it's continuing to plunge. Wind is going to go down. That's the good news.